just go to the, we've got the full screen version, or is that it?
I'm just sharing.
That's fine.
Only you can do that.
Okay, good evening. Sorry about all of that. I think we're there now. And to all those who are on Teams and online, sorry about that. A few technical glitches, but hopefully we're there. Sparks in the Severn Tunnel. What's that about? Well, it's a fitting start, really, because a lot of this is around unexpected consequences. And about a journey really to bring electrification into Wales, and of course the principal connection into Wales is Severn Tunnel in South Wales. So electrification of Severn Tunnel is part of Great Western electrification, and very important. But some things have happened along the way, a little bit like this evening. But that mean that we have to learn from that and take another look. So there we go. Why are we doing it at all? Well, this is an extract of the major feeding diagram of the Wales-England boundary, and Severn Tunnel is there with the little major feeding diagram special water symbol. And the flags, Scotland put the flags on their major feeding diagram and isolation diagram, so why shouldn't we? But what this shows is part of the auto-transformer feeder system that runs the full length of the Great Western electrification, 50 kV distribution, 25 kV supply to the trains, all the way from Paddington through to Cardiff. Now there are just a handful of grid connections and feeder stations to do that, and substantial capacity. It's got the greatest capacity margin of any part of the electrified network. But to do that, there is also a need to think about the resilience of feeding between those, and to be able to move power between grid sections in terms of outages and faults. So many people think, of course, the purpose of overhead line is to put power to trains, whereas actually from a power system engineer's point of view, the whole idea is to move power between grid connections. And so part of the Severn Tunnel's connection role is not just to feed trains in the Severn Tunnel, it is to provide that throughput of power. There is one grid connection in Wales between here and Newport, and there is no resilience to the west of that. Oh, what's happened?
Sorry, Dave, it's my fault. It's Stuart on the line. I took control by mistake, entirely by mistake. Sorry.
Instead of presentation.
That's it. Yeah. Right. Okay. There is no resilience to the west of that. So in the event of loss of the grid connection between here and Newport, then South Wales would be without a power supply. So the answer to that is to bring power through Severn Tunnel from the next grid connection, which is at Melton. Melton's a long way, and that's where the 50 kV feeding comes in. So there's a dual role to this system. The auto-transformer system has auto-transformer feeders that are not part of the contact system. They're quite easy to bring through the tunnel because they can be cabled, and there are cables that carry the dotted lines through the tunnel. And then the contact system, of course, has to be able to run with pantographs. And so that is the approach to feed electric trains into Wales, and we have full sectioning of the tunnel. By that, I mean there are a full set of circuit breakers in a substation at each end of the tunnel, so that the tunnel has its own ability to trip, and also, to the greatest extent, faults outside the tunnel do not affect the tunnel. So there's a substation at Severn Tunnel Junction and another substation at Pilning to do that. So that's the idea. And The capacity is around 30 megawatts. We have the need to be able to move 30 megawatts of power, which is a substantial amount of power, several towns worth of power, through the tunnel, either from Wales to England or England to Wales. And that's really what sets the electrical system design of this. But what do you do to wire a tunnel? Well, here's a tunnel. These are some shots that I took of the Cineri-based tunnel, which is the latest part of what was the Gotthard-based tunnel as it moves down into Italy. It's under the Monte Cineri in the Italian Alps, and it is about 15 kilometers long. It's a lovely alpine, brand new concrete tunnel, all pristine and clean. There's a view back into Switzerland and the Alps. And once we get into the tunnel, what we've got is a rigid overhead contact system. What is that? Well, it's very common for tunnel overhead line systems. It's an aluminium beam, if you like. It's a rigid bar and a standard copper contact wire that sits in a groove in the bottom of that aluminium bar. And that is supported by close-spaced supports. It's rigid, so there's no tension on it. Because there's no tension on it, that doesn't transfer any of the tension wire difficulties into the structure of the tunnel. So it's a very good approach to wire tunnels. You simply fit the supports to the roof of the tunnel, fit the beam, the contact wire sits rigidly in the beam, and off you go. And it's been used in many tunnels around the world, and in fact it's used in a lot of tunnels in this country. It's used in St Pancras, it's used in Scotland, it's used in many of the other Great Western tunnels other than Severn Tunnel. It's in Chipping Sodbury, it's in Newport, it's in Patchway, and on you go. And if you've got this kind of alpine approach with Evian spring water flowing into a tunnel, or definitely none at all, it works very well. But you can see, going back to the time of how do you start thinking about wiring a difficult asset such as Severn Tunnel, it can be perfectly understood how we would have got there, given that that's been used so many times elsewhere. The contact wire, I'm sure lots of people know what a contact wire looks like, but it's a round wire with a couple of grooves cut out of it, which allows you to hold it with clips normally, and for pantographs to then run on it without running into the clip. And in this case, the aluminium beam has a pair of pointed ends that sit in there, and so basically the wire is zipped into the beam system and then is just held there without tension. And that sits in the aluminium beam. Now, of course, an old law of overhead line design is to try and not bring copper and aluminium together. The electrochemical series of copper and aluminium means that if you do, and if there is electrolytic action, if there is something to carry ions between copper and aluminium, then you risk the copper degrading the aluminium, and the aluminium will be sacrificed for the copper. But as I say, it's been used very successfully in many tunnels around the world, and that hasn't really been an issue. And there is a grease applied in the groove that helps keep the electrochemical action at bay. So how do you apply that to Severn Tunnel? Well, it's very boring, isn't it? Here we go. There's an extract of overhead line layout diagram, which is usually full of exciting things such as overlaps and anchor wires and midpoint anchors and all sorts of tensioning devices. This just plods its way through the tunnel, very closely spaced structures. Everyone's got an identity, but they are effectively stovepipes, drop tubes from the roof of the tunnel, very closely spaced, 7-8 meters apart. Not much different really to the dropper spacing that we would have on a normal catenary system. So very closely spaced, lots and lots of structures, but 1,400 in the whole tunnel, all drilled into the roof of the structure. And then that very simple approach of supporting the beam from there. There's cross section. You can see there it is, just pretty much as it is in Canary Tunnel. There's the tube dropped in, drilled into the roof. There's a registration arm swivel arrangement there, and then a little arrangement that holds the beam, and then the bottom of the beam is the contact wire. Really simple. Now, if we zoom in on that, there's the profile of that aluminium beam. So you can see it's a fairly specially made profile. And then sitting down here between these two ends is the contact wire. And that sits on this swivel head here. There's the swivel head. And then we have an insulator, polymeric insulator. Most insulators have now moved to polymeric. They are more robust than porcelain or glass, less prone to vandalism. Of course, that's not an issue down there. And it's been a huge change in terms of the impact of dewirements and not having porcelain and glass insulators shattering and flying around near trains as a result of that. So the polymeric insulator has been a huge success. It is not easy to clean though, which is part of the follow-on story of this. So there it is. Looks slightly different to the Canary-based tunnel, you'll all agree, but then of course it's over 100 years older than that, but nevertheless it's the same thing. Stretching out into the distance there, drop tubes, the supports, registration, the beam, and the contact wire. And that's kind of where we got to with that common sense approach of this has been done before, up till around 2016, 2017, before it went into service. But the atmosphere of Severn Tunnel is known to be quite aggressive. It's aggressive to metal. It's damaging to many metals. So it was really something of a trial to understand how a metal such as aluminium would survive. And it didn't. So within the first few years, and certainly before service, there were problems emerging at that copper aluminium interface. There was also, because the system and the tunnel is carrying diesel traffic still, pollution on those polymeric insulators. They're very good, much better than porcelain, but they do have a drawback compared to porcelain because they don't have that nice ceramic shiny surface that you can clean. They are silicon rubber sheds, and when carbon and soot get into the surface, then they're extremely difficult to clean. And if a conducting material such as carbon covers the whole surface of the insulator, then you risk partial discharge and then eventually flashover and failure. And if you've got 1,400 insulators in there, there is then, of course, a maintenance liability with the potential for insulator failure. But that was one issue. The corrosion started to become a significant point, even by 2017, 2018. In fact, there were sections where the aluminium beam had corroded when in contact with the copper to the point that the copper wire fell out of the beam. So even at that point, something had to be done. Now, that raises the issue of what do you do? The aluminium will always be susceptible to electrolytic corrosion in contact with copper. Even copper and steel will have electrolytic corrosion if in an electrolyte environment, which there is. So do you take out all of the aluminium, even though the aluminium away from the copper wasn't in bad condition? Or do you take out all of the copper? And there have been some trials previously, not in this country, but with an aluminium contact wire. Now, of course, aluminium contact wire is not that popular for the obvious reason that you run on it. Copper is very hard wearing, so having an aluminium contact wire is inevitably not going to last as long as a copper contact wire. But with corrosion occurring, and with the life of the beam system, the rock system, being quite limited, then something had to happen. And actually, the aluminium contact wire was a good move at the time to allow that corrosion to be removed, to allow a wider study piece of work to be put in place to understand what the long-term answer would be. So 2018, the whole thing was replaced. The beam was replaced in sections where it had corroded. The rest of it was left there, but the full contact wire was removed and replaced with a new aluminium contact wire, accepting it probably wouldn't last the life of a copper contact wire. And that got us to the point of electric services in 2019 between Wales and England for the first time. So from our point of view, a success, but of course, some issues to deal with. If we have a look at some of the other points, along the length of the tunnel, there are expansion joints that allow the aluminium beam some movement. And those, you can see, sometimes are prone to seize. And if you look there, this one on the down line looks okay. This one has some buckles in it, and that is no different. That's why I brought it to a PWI event, because no one knows more about that kind of buckled rail than the members here. But that is just an example of a seized expansion joint, which is another maintenance overhead.
Was that corrosion the main issue as well again?
Yeah, some of it, yes, but then they're just sticking over time, and the environment has to be released, and releases with some force. So there's another problem. And what I don't want is for this presentation to be a whole catalogue of photos of bad things, because overall this has been a successful move. But I want to show this one because that is probably difficult to see what that is, but that is the underside of the aluminium beam. That is it. You can see the saltwater atmosphere. You can see the effects on the aluminium itself. But you can also see here, that is the contact wire. And that is of course the second contact wire is there. The copper contact wire is removed. The aluminium contact wire was installed, and that's the running surface of the contact wire. So yes, it gained some time, but something else had to be done. So the approach was to really take everything off the table, accept that good people made good decisions on what had been done elsewhere, and used established practice, but established practice doesn't work in Severn Tunnel. And so it needs tangential thinking. What do we need? Not what has been used, but what do we need for this particular environment, this particular tunnel, that replaces that. And of course, there are some key pieces of learning from this. Firstly, do not put aluminium in the tunnel. It's an issue of bringing it near copper, but copper is, the predominant electrical conductor, and it's far better than performance of the aluminium contact wire. So a copper contact system is needed. They're simply not going to work. Secondly, aluminium, regardless of the interface, suffers in that environment there. So aluminium's out. That's a kind of red line. Secondly, it comes back to those drop tubes and the work that was done to install them. And there are about 1,400 structures drilled into the roof of the tunnel. So one of our principles is that we don't want any more. That's enough drilling of the structure of the tunnel. In principle, it should be enough to hang anything off. So what is it that we can put on those steel tubes that are good themselves? Those are the good part of this. how can we move on without a complete removal of everything that's there, and get the best out of where we were. And so we pushed for any idea, with a view that sometimes perhaps we moved too quickly to one answer, and that there was a period over 3 years ago now where we encouraged any kind of approach. What could we do with the beam? The beam itself works. Could we make it out of something else? Could we make it out of plastic? And we had a whole load of clever people who understand plastics better than us look at different types of plastics that would be polymers that would be suitable for that sort of environment. One of there is polyether ether ketone, PEEK. Suitable for the environment, but what would be needed to give the strength that we've got with the aluminium? And you can see some rather bizarre looking cross sections there. And so those didn't move forward, but the idea of don't be fixed by anything traditional and let's see what the art of the possible is was a good idea. The other problem, of course, with one of these is that should we move away from this approach to these cross sections, that would need a whole new manufacturing approach. There is no factory that makes that. So does that mean that we have to support manufacturing and production just for one tunnel and all of the impact that comes with that? So it didn't make the cut, but it's good that we weren't constraining ourselves to anything traditional. Here we go. So there's a design that was done for us, bizarre teardrop looking rock system hanging off an existing swivel. So yeah, but no. Another idea is, could you make it out of a material that also helped conductivity? Because the aluminium carries a proportion of the current. It carries a lot of the current. It's not just in the copper. So what else could you do that with that has some strength in it? And so the idea is put forward, how about carbon fiber? So a carbon fiber beam made to a very similar profile, and then a copper contact wire. Of course, carbon fiber, there'd be no electrolytic corrosion. Could it work? Back to the same issue of tooling and manufacture. Carbon fiber can be made into lots of things, but making 14 kilometers of it on the production line would be a challenge, and that was definitely a stumbling point. But then we also had this, I think the heading's wrong there, but this is about a composite mast. So around the same time, we were exploring carbon fiber. That's a carbon fiber overhead line mast. And that is also in Wales. It's still there, actually. It's between you and Newport. And the idea was that a carbon fiber mast is light compared to steel. Could it replace the steel of masts? And so, not connected to the work on Severn Tunnel, we're looking at the feasibility of this. And this arrangement here is a standard cantilever installed on a single mast that's made out of carbon fiber. And there is a cable that you see runs up here on insulators and then is connected to that mast bracket at the top. That's there so that we can understand what would happen if we built a carbon fiber mast and, as happens, there is a fault to Earth via the mast. So that cable runs off to one of our substations, and the idea was to put 12,000 amps into the carbon fiber mast and then see the outcome. There we go. That's the outcome. The sound hasn't come out with all of our IT issues, but I'll try and wind that back. Let's have another go. Right, was I in the way there?
Without bang.
That's a bang. That's a earth fault. That's good, and it tripped, which is even better. So that's good. That's let's just stop that. There we go. That's an earth fault onto the new carbon fibre mast, and then if we look at, here we go. We look at the post-mortem on that. You see that the mast bracket seems to have grown a little moustache there, and that, if you close up on it, is an exploded set of carbon fibres that have come out of the structure of the mast. That's where the fault current went in on this bond, and that's the damage it did to the mast. And that kind of settled our view that compared to the simplicity of steel, then carbon fibre might be very strong, it might be very lightweight, but it certainly isn't going to survive the sort of short circuits that we commonly see. And for all those reasons, all sorts of different rigid systems made of polymers, carbon fibre, were rejected. And in that early analysis, this is another approach that was put forward, which is to use something quite traditional, actually, which is the glass fibre bridge arm, commonly used from British Rail days on bridges. It's basically a single arm. There's a little arrangement here to support it off the back of the tube. This was put forward, and it's simple. Of course, it keeps the copper away from the steel using the bridge arm, and seemed to have something about it. That's how old this is. There we go. Balfour Beatty power construction. That's part of the traditional overhead line design range, and you can see the bridge arm there. So, is it possible to do something very simple with just a contact wire on a bridge arm using components that have been around for decades? Don't know. That's one conceptual idea of what could be in there.
That's using the tubes, the existing tubes that have been put in,
The existing
just
tubes,
replacing the bits on the end of it.
some sort of bracket that would get you the length, and then a simple supported contact wire. Certainly worth exploring, and that's kind of where we've got to. There's a close-up. That there is the clamp that holds the auto transformer feeder. That's the insulated cable up there. That's the earth wire. That's the drop tube, and then maybe some arrangement like that or similar to it. How would that perform, and how would you terminate wire in a tunnel? Well, one of the challenges is the rather wild throwdown view of, could we just run one wire all the way through the tunnel, 7 kilometres long? And normally would not do that because once you start getting over 1,200, 1,500 metres, the amount of expansion and contraction and long track movement limits what you can do, and you start affecting registrations, you affect cross track movement. So wire runs are terminated because of that. But of course, in the tunnel, the environment's different. To some extent, temperature is far more steady. So could you just go all the way through the tunnel? What would be the point of that? It's a bold overhead line design for sure, and we haven't done that before, but it would avoid having to put anchoring points, tensioning equipment inside the tunnel, and as we have learnt the hard way, putting anything in that tunnel that is complex or has lots of components or is a sophisticated mechanical system is basically asking for a level of bad luck and trouble. But how do you understand where temperature is? Well, there was some temperature monitoring done quite a while ago, actually, as part of the first design of the tunnel, and it was done at a few locations through the tunnel. Now, what it shows is if we take the mean, the minimum, and the maximum over the monitoring period, then we've got maximum temperatures here that are not much more than 20, but some spikes. And ambient temperatures of 40, 45, which seem incredible, really. But this lines up with the shaft that said, look, these are the portals. So it could be that we've got ambient temperatures that high, although it sounds a little bit too high. But nevertheless, could we do something with that data to just explore the idea that we looked at? And that characteristic there is an interpolated view from those points. We haven't got points all the way along the tunnel, but we know where every structure is. We've got locations of every one of the 1400 structures. So if we take into account the peaks and we know where there are measurement points here that are much lower, could you interpolate a curve that is the best fit on the data we have and see what that does? And also in parallel, we started some new temperature monitoring, which is ongoing to get a whole new set of data over the whole year that will produce a much better version of that. Well, one of the great debates of overhead line standards is what the temperatures actually mean. There is a 38-degree temperature often written, but of course, when you get into the mechanical limits of overhead line, you also have to take account of the fact that that is about the wire temperature, and the expansion is about the wire temperature, and actually the air temperature is always going to be lower for as long as you're carrying current. So if you carry current in a conductor, then you get I²R heating. That means the wire is always going to be hotter than the surroundings. Then it loses energy, heat energy. It loses it by radiation, it loses it by convection, and it loses it by conduction through the air. And if it's outside, that's countered by solar gain, which takes you in the opposite direction, which heats up the wire. So the link between wire temperature and ambient temperature needs to take account of a current flow. And so we've got a current flow there, 300 amps, and that comes back to our original starting point of what are we going to use the tunnel system for. And so we can then go from those ambient characteristics, albeit they are based on some early measurements that were in spot locations. Well, what would that mean if we transferred that with that current into the wire temperature? And that takes us up a bit higher. We're now between 60, 70 peak and 40-degree wire in that stable area. And if we then say, right, that is effectively the temperature of every single span, we can now go down into that data and say at every structure, at every midpoint between every structure, we can take a mean temperature for that span, only 7 meters long. We've got our own cheap and cheerful version of a finite element model where we can look at the expansion on a span by span basis. And so we can look at how much the whole thing moves based on it being, you can see there the overlaps even. There are structures that are much closer together. You see those spikes where you can see much less movement. And that is the amount of expansion in millimeters based on a 20-degree set of temperature and that temperature range. So as a first pass, and there are broad assumptions in it that we've set out, that allows us to say, well, if that's happening on a span by span basis, what would happen if we added them all up? There we go. And then you can get a sort of cumulative long track movement. And this is done with the simple assumption that you pin it somewhere in the middle and allow the ends to move, because if there are going to be moving anchors, then they would be better done outside of the tunnel. So that's pegged, and then that's the cumulative effect of all of those tiny movements. On this basis, we've got 1 to 1.5 meters, which is encouraging to allow more to be done. And then total along track movement, tunnel centre, midpoint anchor gets us there. So that was just a starting point. Where do we go next? Well, there's a lot more to this than just taking spot temperatures. So we need that much better temperature profile. We need to explore that 40-degree ambient, which seems high, particularly for Wales. We also need to understand the other aspects of overhead line design. We need to understand how a simple system like that, which has simple maintenance advantages, would actually run. So dynamic modelling of the pantograph performance on something like that. That's being done right now. This has moved on, and lots of good people are doing that work. So dynamic modelling is coming. And then
the effect of that effect on the wire of a train being
yes, and how the arms would respond to it, and whether there are resonances. That, of course, the resonances are helped by the fact that you see the unevenness in some of the spans from the original drop tubes. So we haven't got a regular fixed spacing, which helps break up anything that could be that. But it needs mathematics. It needs analysing with a view, and we're currently looking at how we would do this to try and get a level of a trial of this solution or whatever the preferred solution is by next summer, and to put in a trial. We would love to have one full road actually sitting as a full trial of this, and then to tweak that, to learn from it, understand what's not working, and then move on to 2026 to complete the work. There's a lot to go between now and then, but that's effectively the journey that we've been on from those early days of what seemed like a great idea, taking what all those brilliant people in SBB and Swiss Railways have done, applying it here, finding out we had to go somewhere else, and moving on from it. And that's Severn Tunnel. I just want to, how long have we got? Okay. So as well as that should get us to a point with this work and all the following work that is to come, of a stable mechanical system with much better running performance than we have today, and stability for the future of Severn Tunnel, and that electrified link between Wales and England that is key to resilience of the power system and to continuing to run electric trains. We've got, of course, IETs, which have diesel engines, but we also have Electrostar Class 387 services. Not many, but they are used to support events in Cardiff. They are a very effective electric EMU, and the tunnel is of course critical to an EMU without diesel engine operation. But where do we go next? So in terms of our design beyond this, well, the future's changed a little bit because the IET, yes, had a diesel engine on it, but all around the world now we see the advent of battery trains coming in. Hydrogen battery has been a debate for over 5 years. We've been doing some work in the US supporting battery train analysis over there. And it comes back then to, we bring in a battery train, what do we do to work out where we go with it? We can't just do the same old system design. How do you use the battery on the train? What does the charging mean? Charging rates, discharge rates. There's a whole new set of questions that we didn't really have before. So this is the sort of thing that is becoming commonplace now that we weren't looking at 10 years ago, didn't really care. And that's energy consumption as a cumulative plot. That's a journey. It's actually on a line in South Wales. It's one of the valley lines that's not a core valley line. And it shows the energy consumption through the journey, and you can relate that to all the factors in a train movement model that you would expect. And those are the usual ones. Of course, gradient, changes potential energy, line speed, kinetic energy, stopping and starting. If you brake, you never recover all the energy, and so we have to put more in. So the number of station stops affects the total energy profile. Auxiliaries. Auxiliaries are never really a huge factor against the large traction power, but that was back in that world when traction power designers only thought about the big traction.
Yeah.
And if you are sitting there on a battery for say 3 hours on auxiliary load, then that is a major impact, because that is ticking away all the time. The heating, the air conditioning, depending on conditions, of course, very variable. So there are new challenges in that. And also, what do we do with regenerative braking? Well, of course, the options there are now that you can take energy out of the motors, the braking system, and put them back into the battery. You don't have to put them into a Rio brake or into the wire. If you don't have wires, you could recharge the battery a little bit. What effect does battery charging from regen have? So we've done a lot of work on analysing that. And what does the impact of charge rates have? There are lots of things you can do with charge rates. So charge rates are measured in Cs, where you take effectively the capacity of the battery. If you charge it at 1 C, you fill the whole battery in 1 hour, and that, depending on the size of the battery, that then sets the rate. And there are very high C rates. There are C rates of 4 and 5 that are being put around, and that gives you very effective charging, but it also has a longer term impact on the chemistry of the battery. And so there was a balance between fast charging and impacting the life of the lithium-ion battery. Having said that, lithium-ion chemistry is changing very quickly. We're already seeing combinations which weren't here 5 to 10 years ago, and we're seeing densities increase. So the amount of kilowatt hours, megawatt hours that you get for every kilo of battery mass, or every cubic meter of battery volume density, or mass density, is increasing. We're getting more kilowatt hours, and we'd expect to see more of that. And of course, that's not driven by the rail industry. That's driven by the automotive industry, by mobile phones, and all of the other things that are pushing lithium-ion technology. But it's changing very quickly, and costs of that storage are falling as a result. So this is a whole new challenge to us as designers. I mean, that starts to make us think, where do you go with an overall decarbonisation model? Because it's no longer as simple as saying we will just wire a line and run electric trains, or we won't wire it and run diesel trains. We can now choose to wire some of it. And which parts do you choose? And that comes back to the variability of the so-called STK, single track kilometre cost of electrification, which has a huge number of factors in and is very widely debated. But we can pin down some of the things that we try and avoid. We try and avoid reconstructing bridges. Those have been very expensive. We try and avoid very difficult station areas. So we know that there are areas where you spend a lot of money in a relatively short distance, and there are other areas where open route is relatively inexpensive to do it. And the battery allows new models to be built to understand how could you lower the overall STK rate whilst targeting where you go. And here's an example. Pushing on in Wales, this is some work we did earlier in the year. and this is looking at the North Wales coast. It's looking at battery electric multiple units, BEMUs, are now the in vogue term. That wasn't there either a few years ago, but BEMU is now fairly established. And that's a passenger service which reflects the existing crew through to Holyhead. And what's going on here? Well, something's left crew, and you can see the battery energy percentage falling. It's falling in steps, so something's going on.
Vertical scale is energy.
Exactly, and the battery energy is falling, so that's the battery there. Then we get to some location here, and it starts ramping up because you control the charge rate, but you're now on the wires. And so over time, we see that the charge level is recovering. And then you reach maximum charge, and of course you take no more charge. But that means the current draw here is a little bit different to the current draw in there. And then you come off the wires and we start heading towards Anglesey, and it drops again. And then there's a little boost as we get into Holyhead. And that is a typical profile of trying to look at this balance between being on wires, off wires. What is going on when you're on and off? It's not the old current, because we now have traction current and we have charging current. But when we get to this point, we don't have charging current, we just have traction current. So it's a changed model approach compared to what we're used to in the past. And of course, there are trains coming the other way doing the same thing. And just to be slightly contentious, this is a freight model, which is a container train that does effectively the same journey but doesn't call at all those station stops. And that shows how a relatively heavy, couple of 1,000-ton freight train could also do it. Now, battery size of this is bigger than the battery size on the passenger train, but nevertheless, densities are increasing. And one might suspect that on a 2,000-ton freight train, you could find more space and have more availability for more mass of a battery than you could on a passenger train. You don't have to put it underneath the seats or in the equipment compartments. And in fact, even Lego had this fact in the 1970s, where the Lego train had a little battery tender that pulled along behind it with some D cells. And so that concept is not as out of court as it might seem. And in fact, just the other week in Innertrans, we're seeing hydrogen tenders being put forward for freight trains. And so if you can have a whole wagon that is a hydrogen tender, you could in principle.
Basically a tank wagon carrying your compressed hydrogen.
Correct, but you could use the train with a battery wagon.
Yeah.
It's the same principle. So that sort of sets the challenge of the future. And that changes dramatically where we look at power supplies, where we get power supply from, how services interact, this issue of charging and not charging and then discharging. And then here we go. This is a little simple branch line. It's actually normal, but this shows the regen quite clearly. You can see at the breaking points, the energy actually goes out.
Station stops, yeah.
The station stops as you're coming in, you just recover a little bit of energy. So that changes the profile and is part of assessing it. So in the future, I won't dwell on this too much. What we're also looking at is stripping out what would have been all those awful old substations and replacing most of them with just overhead line switches, rationalization, as it's called, making use of the protocols of digital substation technology, where instead of traditional substations standing alone and working out where faults are, and I'll just move on to this. That's a typical back of a protection panel in a conventional substation, wires for everything, pair of wires for every single function, and another pair of wires for every other function. But once you've wired it, That's it. If you want to change the functionality, you have to go rewire it. Whereas, of course, in any other walk of life, that would now be done by data flows. How do you do that? Well, you replace what used to be protection relays by something called IEDs. That's the standard came up with that name, not me. Unfortunately, intelligent electronic device. And then you run effectively a data bus through the substation. And what we've done for the first time in Great Western is take that concept outside the substation. So we have substations that talk to each other during faults, during 10 milliseconds of a fault, and they pass information of fault. So the protection system is now cooperative. Instead of everywhere having to work out where the fault is, if the fault is on the down main, then the next substation that's connected to the down main doesn't have to decide itself where the fault is, which is the traditional approach. It gets told, and then they all work together, and that's an effective, rationalised approach. And it means we need less circuit breakers, so we need less substations. It all becomes a much cheaper approach to electrifying. And just a few slides to finish off. This is the standard. I bang on about this all the time. People who know me will be bored of my ability to turn any discussion back to 61850. But the standard that sets that digital architecture for substations all around the world, transmission and distribution, is IEC 61850. It hasn't got a better name. That is just stuck. So people just call it 61850 now. And it's a standard data architecture for substations, for power systems, taking on board some of the criticality of timing and messaging. So there are all sorts of constructions inside 61850 to allow trips to operate fast, but to do it over Ethernet type structures. And indeed, the world's moved on from that, because instead of just having IEDs, there is now another layer of bus that has moved on since Great Western. This is moving so fast that Great Western is now old. So that extends data networking down to transducers. So current transformers and voltage transformers, which are really the eyes and ears of a power system. That's where you get your information. What's the voltage doing? What's the current doing? You would wire them into the IEDs, and then the data would go. What if you could digitize it right at source and have the process bus, which operates down at that layer, take sampled values of current and voltage, and then your protection relays can pick it up from anywhere. They don't need to be in the substation. This is a merging unit, which is one of these new gadgets that merges all of these sampled value data streams, all the voltages, all the currents from a substation, you merge into a data stream and send off down the bus. And this is in our feeder station. So we're the first to fit process bus technology. Great Western now has it. It's post-WEP. We've done it in the last few years from here. And that means we have access to sampled values. And it actually means that we don't have to put protection relays wired to the current transformers, because you can go and get the data from a fibre. And if that's the case, why put the protection relays out in the substation? In fact, why have the substation at all? Why have somewhere we have to drive to and have to analyse protection relays and maintain difficult weather conditions? This will be a game changer to the onward march of electrification, cost cutting, and just making the system very much simpler. And then finally, for those that follow RSSB research projects, piece of work we've been doing over the last year or so is exploring what happens if you put this sort of technology on a train. Because trains are really very sophisticated power system elements. A modern train, 7 megawatts, and 7 megawatts is bigger than some towns. And that's all within a train. So this sort of communication technology could really change things, because you could actually talk to the train in terms of perturbations. The train could talk to you over this data network. where we struggle to understand, is that current a fault or is it the train? And where we get false trips. Well, the train has to be there to do it. So if the train can contribute to that discussion, if it's not there, it must be a fault. And that's the sort of data analysis that we haven't been able to do in the past. And that will change at a software UML diagram of where this goes, and we start adding training to the substation approach and call the train a dynamic substation. In other words, it's a substation that can appear and disappear on the power system, and that allows you to fit into the abstract world of it. So that's it. We start with some real tough civil and mechanical challenges and chemistry, really, of how we take Severn Tunnel, well over 100 years old, and the challenges of bringing electrification into Wales. But we think we are well on the way to tackling that, and we understand at least where all the problems were. And then from there, we move on to further decarbonisation, England and Wales, but battery technology, 6950, more use of sample value data, all about reducing the overall cost of that decarbonisation and removing diesel and moving to fully decarb systems. Thank you.
Thank you. Wow, you'll be my comment. Right, have you got any questions? Yes.
I think just briefly remind us exactly what conductor have we got in the Severn Tunnel at the moment?
It's the aluminium, excuse me, it's the aluminium rigid system, the original aluminium rigid system.
Yeah.
With the aluminium replaced contact wire. The original copper contact wire was taken out, and it's the aluminium wire that will now stay there until we come up with
We've got an aluminium contact wire for the moment, at least.
correct.
Thank you.
Any other questions? Yeah. Yeah.
Dave, I'm going to keep this really simple, so you know how little I know about all of this. I haven't mentioned AI really at all. And what's it going to look like in 20 years? Is it going to be a slimmer, cheaper system?
Well, that's what
Less galvanized, less sort of.
that's what the final part of this all is. That data technology. We could say AI. I think a lot of the time we say AI almost without knowing what we mean by AI. And AI, of course, is very good at taking lots of available data and training itself. Where you have very sparse training sets, then it's more difficult to understand where you go. So natural language models are obviously the core of AI at the moment, ChatGPT and all of that sort of thing. There are other things in terms of pattern recognition where AI is unsurpassed. But you've got to get to that point where you've got data. And so I think the next stage of this is that data, digital substation approach, easier to move data, not having your data sat out in remote locations that can only be accessed by a vehicle. And then almost certainly there will be overlays of big data analysis and
Well, I presume, because you haven't mentioned it, there'd be no similar problems in any of the other tunnels, because they haven't got the saline atmosphere.
correct. To the most extent, yes. I think there are lower levels of corrosion. It would be good from our point of view. Nothing is like Severn Tunnel atmosphere, but if we can find a really robust solution to this, and also reduce the maintenance burden, something that doesn't need lots of cleaning, doesn't need lots of inspection for fear that something will fail, we at least have something on the shelf that could be applied to any other tunnel where this happens.
No matter how bad it is. Yeah.
Yeah, and if it works in Severn Tunnel, I would wager a bet that you could apply the same solution to any other tunnel in the country, pretty much.
Yeah. Okay.
Okay.
Clearly, getting rid of diesel trains would be really good at it, well, wouldn't it?
It-
A step in the right direction.
Yeah, there were the chemical analysis that was done originally. Started off with a view of we're looking at the iron that runs down the wall and the chemicals that come in from the water. So it was all starting from the point of view of what's in the water. A lot of the chemical analysis led back to carbon. so a lot of it is a corrosive atmosphere.
Yeah.
So certainly full removal of diesel will help.
Any other questions? Andrew?
Going back to the aluminium contact wire that you've got in there now, I've got no idea how long a normal contact wire would last, and how much shorter is the life of an aluminium contact wire. Putting it in layman's terms, say the service out to Airport Junction, what's the life of wire?
Considerably as the answer. Well, I mean, there is contact wire that has been there for decades. Of course, it's all about pantograph passages.
There's rail that's been there for decades.
Absolutely. So getting one measure, but there's certainly decades of use from copper contact wire is not out of the question. The aluminium wire will not do that. We will need to do something about that system this control period.
But so we're talking probably every 10 years of the absolute
5 to 10 years, 10
Yeah.
probably at the outside, if this were to be replaced with aluminium wire based on the traffic levels that are there. So very much shorter.
Okay, right. Any other questions? Do we have any questions from anyone online?
No.
Okay.
Well, actually.
Hmm?
I was going to ask, but I think it's already been answered though. So that because of the work you've done, has anyone else shown interest in it simply because they've got problems and they're thinking, oh, I wonder if whatever you do in the Severn Tunnel.
We've got lots of calls watching what happens next from others in the country that have a similar system. I think I don't think anyone's got the extent or problem with it. And to be fair, the rock filling has worked well in many tunnels, so it's not as if this is a dead duck. It's worked. It just hasn't worked as well here. So people are watching, but I guess the test will be what we do next, and then whether that is seen to be simpler.
Scotland, the first one, was it?
Scotland have
Mount
got it.
Tunnel? So just coming into Waverley Station, it's not a particularly wet tunnel, and it's only got quite shallow cover over, but it's been working right satisfactorily in there from day one. So
Yeah, and in Glasgow they've got it.
Yeah.
But
right. Any more questions?
anything online? Or any of that?
No.
No.
Right, can I
No.
request ask Andrew to propose the vote if they?
Just got one.
Mhm.
You've got a question?
Yeah.
Go on, take that.
During the test of the carbon fibre mast, was cognizance taken of the way in which this predictable failure mode of carbon fibre is dealt with in a similar way to lightning strikes on certain aircraft, 787, by weaving in a conductive path into laminar mesh, or by providing a common bond which attaches to the AEW and or structure rail bond? Are you reading that, Dave, as well?
No, but I'll answer it as best I can. So the aerial earth wire, the earthing connection was connected to the mast bracket, as would be the case. So I think that's fair. The weaving in of a mesh, no, but we took the mast as produced really, and I guess if a simple carbon fibre structure that had something else built into the manufacture of it and didn't affect the cost and all of the other benefits put forward for it was possible, then it's possible someone else could have a go at that and see where it goes. But it seemed to be one step on in the complexity of the construction from what we had. But in terms of the earth connection, I think it's fair.
Okay, thank you. Right,
Nobody?
anyone else? Yeah.
Right.
Andrew.
Okay. That's the moral of this story is don't sit next to the chairman. getting towards the end of the meeting. And Dave, it's a pleasure to give you a vote of thanks for this meeting. As a civil engineer with a few years service, I've never had much to do with the sparks upstairs. And in fact, it was only at Round Live this last year that I actually got hold of a piece of contact wire that was there as a short piece. I could see both ends. I actually got hold of it to actually feel it and touch it, and the really touchy feeling. It's dead difficult to get up there and have a look at the kit. Ours is quite easy to, I don't know, as long as it's not a 750 through it. But Severn Tunnel is, as I know, because my first meeting with Emma was about 25 years ago or something, looking at water response in Severn Tunnel when she was
ATM,
Principal Road.
Yes.
And it was a job for Scott Wilson looking at the waterproofing of the Severn Tunnel and where all the bits of corrugated iron had disappeared to, and you may have well seen it in your work to date. So yes, I can see all the problems and the challenges and see where the whole scheme absorbed loads and loads of money and it prevented it from getting to Swansea, but that's another matter. So I'd just like you all to join me in thanking Dave for a most entertaining and instructive lecture tonight. It was great. Thanks so much.
Okay, thank you.
Thank you very much. Right, so next meeting is
Good question. 4 weeks today.
4 weeks today. Yeah.
I've lost my piece of paper now.
That's it, all right.
11th of November, that will be, won't it?
11th of November, Decarbonising for Sustainable Track by Darren Sharp.
So Darren Sharp's in our one of the engineers who works on supply chain. So he's got there's a lot, Network Rail's doing a lot of stuff in trying to decarbonise things like rails and concrete sleepers and things like that. So I'm sure that'll be a really interesting talk on where we're going with that. And again, we'll be back to composite materials and things like that and new ways of using them rather than just trying to replicate what we always do now. Having a look at new ways of using those materials in a more efficient and energy efficient way. Okay. Well, I'll see you all then. Yeah. Thank you. Okay, thank you very much, Dave.